So the last section that we talk about here, 2.8, the last section in chapter 2 that we talk about is called related rates. And this is not a new idea as much as it is just a collection of this type of problem. So related rates is a type of problem, right? It's not like learning about a kind of derivative and like chain rule and all that stuff. It's not a new method to do anything. All it is are a new like type of problem. Why do we call them that? Well, because they're word problems and they are a lot messier than most of the other problems that we deal with, right? Um, okay, so I'm going to, in theory, I could end the video here and say it's a word problem, do it. But these are messy, and it's very much worth like actually like doing, like seeing someone do. And the funny thing is that um, these problems are almost standard in a way that it's normal to have almost the same kind of situation, just worded differently, um, or given different values. So, like the things that we're going to do here end up looking almost the same as questions that are on the homework. The numbers are just different, and the functions are like slightly tweaked. So, okay. So the first one that I want to do is this problem that says the radius of actually, hold on, there's a smarter way than writing down this entire problem and wasting a lot of time on that. Uh, okay, boom. All right, example of an expanding oil slick. The radius of a circular oil slick expands at a rate of 2 meters per minute. Okay, so right now let's try and draw our scenario. So we have an oil slick and a radius, right? So we have some circle, right, R, and it is expanding. So the length of that radius is a function of time. And now we have our oil slick that is possibly the worst circle I have ever drawn, but we can pretend that's a nice circle, right? So the question wants to know, where did it go? So our question says, how fast is the area of the oil slick increasing when the radius is 25 meters? So, first of all, it wants to know the area, well, how fast the area is changing. So we know that we're going to need to write something with area. And we know that there's going to be some time, I'm going to call t naught, where the radius is 25, right? So it says, how fast is the area of the oil slick increasing when the radius is 25 meters? So we want the change of the area. So in order to find the change of the area, we need to find the formula for the area in the first place, right? So our area of a circle is the classic pi times our radius squared, but we recognize our radius isn't just like a solid static number, it's not a constant term. Our radius is changing over time. So I wrote r squared, but it would be more accurate in this case to say r of t squared. And we also should probably recognize that our function is also in terms of time, right? This is now a function that we're making out of our area formula. So if we want to know the change in area, well, the change of a function is the derivative, so we want to take the derivative of this function. So, no, I don't want to look at Spotify Premium. So, we need to differentiate this. Now our constant multiplier rule says that pi should just carry along. And now we want to take the derivative of r of t squared, and that is a function that is being squared, so we have to use the chain rule. So the outside part is squaring, so we're going to drop the 2 down and subtract 1 from the top, leave the inside alone, and then multiply by the derivative of the inside. And the derivative of r of t is, well, r prime of t. So we want to know the change in area at the time t naught, which is just me giving a name to the input whenever the radius is 25 meters. In fact, I'll go ahead and write this, right? This is meters. Area should be in square meters. So, um, let me go back to this problem. It says the radius of a circular oil slick expands at a rate of 2 meters per minute. So the change in radius is 2 meters per minute. Well, is there anything that I have that relates to the change of radius? Oh yeah, that is exactly r prime, the change of the radius. And I just read it, but I already forgot. Did it say 2 or 6? Okay, 2 meters per minute. So this is kind of telling us that our time units are in minutes for one. So we can say a prime of t. I'm going to move this to give us a little bit more space. A prime of t is in square meters, is the output per input is minutes, so square meters per minute, right? So again, a prime of t, we plug everything in. So 2 pi times 2 times r of t naught times r prime of t naught. Well, again, I just read r prime should be 2. By the way the question is set up, r of t naught should be 25. That's what t naught, how we picked it, right? And then times 2 times pi. So we have all of our variables figured out. 2 times 2, right, is 4. So pi times 4 times 25, well, 4 times 25 is 100. So this is really just pi times 100. Very good. So this is kind of the example where it's not too bad, right? There's not a lot of confusion about where to go. There is immediately this area function for a circle, right? How fast is the area changing means we immediately have to look at, okay, well, how do I find the area? You know, we know we need to look at the area. How fast is the area changing? Well, change is derivative. So this one doesn't take a lot of like nuanced thinking about how to get the thing that we need, how to set it up in a nice way, like some of the other problems will. This one we kind of immediately just kind of read it and hopefully maybe can see that it wants the area. So now it has a part B. If the radius is 0 at time t equals 0, how fast is the area increasing after 3 minutes? So this is saying if r of 0 is 0, can we figure some information out from that? And I insist that yes, actually we can. And this is kind of a new idea to us, right? So r prime of any value is just going to be 2. That's what it told us in the problem, right? It said the radius of a circular oil slick expands at a rate of 2 meters per minute. Well, what kind of function has a derivative that is just a number? What kind of function has a constant slope? Well, that is a line. So because my derivative is just 2, that tells me my original function R is a line with slope 2. So if I have y equals mx plus b, then I know my m is 2. So the only thing that would be unknown is whatever this plus b part is over here. However, since I know plugging in 0 gives me 0, then I know 0 is equal to 2 times 0 plus b. Well, 2 times 0 is 0, so 0 plus b is just b, so 0 is equal to b. So it turns out r of t, oh, r of t is 2t plus 0, which we don't even need to write. Okay, so r of t is just 2t. So now, the question it asked us was, if the radius is 0 at time t equals 0, how fast is the area increasing after 3 minutes? Well, if area, well, we want to know how fast the area is changing after 3 minutes. So the work that we just did told us the area, the derivative of the area should be our function pi times 2r of t times r prime of t, right? Well, this means that I can plug in my function r of t directly in here. And also r prime of t is already 2, so I get to plug a couple of pieces in, right? Pi times 2 times 2t times 2. So I can combine all these 2's together. 2 times 2 is 4, times another 2 is 8. So 8 pi t. Well, what is my time? The question said 3 minutes. So a prime of 3 is 8 pi times 3. And 8 times 3 turns out 24 times pi. So my answer ends up being 24 pi. Fantastic. So these are two slightly different questions, and the ability to recognize, hey, if my derivative is a constant, then I must be a line, is a new idea that more so ties into like what we're going to do later with like integrating, which is why part B is just slightly messier. But you can also think of it very practically, very literally. You know, if it says that your radius at time 0 is 0, but you increase with what? 2 meters per minute, then for every minute you're going to increase by 2 meters, then that should tell you maybe intuitively that after 3 minutes, yeah, that this length should be 6, right? 2 plus 2 plus 2 give me 6. So even if you didn't really totally connect, you know, r of t turns into 2t, there's still a very like, perception-based way to approach this, where maybe you only end up simplifying this into 4 pi times r of t, but then you realize that r of 3 needs to be 6, so then this is 4 pi times 6, which still turns into 24 pi. Right. We're not so entirely strict on how these things need to come about. I did it the very mathy, function-based way, but if you just understand what's happening well enough, then that would be fine too. So even if you didn't make the observation that it must be linear, it turns out that the way that you set this piece up, um, you are saying it's linear, just in actual human terms instead of the definition of a line, right? So you understand it well enough even if you do that approach too. So either way is valid and very good, I'd say. Okay, so that's part A and B, except I neglected something, right? This is a word problem, which means we are supposed to use units. So because both of these were A prime, and I did take that second to say that A prime is square meters per minute, technically my answer isn't pi times 100 on that part A. It's pi times 100 square meters per minute in the second part as well as A prime. So this is 24 pi square meters per minute. Um, some people would write that like this. That's great. Whatever you want. You can write out the whole thing, including PER instead of the slash. Yeah, very good. Okay, so now let's consider this question. A 16-foot ladder leans against a vertical wall. The top of the ladder slides down the wall at a constant rate of 4 feet per second. Okay, so let's visualize this situation so we can maybe see what's happening. So we have a ladder leaning against the wall of some building. However, this ladder is sliding downwards, and it said that it's happening at a rate of 4 feet per second. So 4 feet per second. Well, what does this look like over time? Well, we recognize, this is standing on flat ground, right? So as our ladder is falling, the ground and the wall aren't changing, but my ladder doesn't like shorten in length. So, nope, that is not flat ground. So because the way that the ladder is falling, it's keeping that same height that it has and is slowly going to eventually like hit the ground, right? Eventually the ladder is just going to be like laying flat on the ground. So not only is it like falling like vertically, right, the top of the ladder falling at 4 feet per second, but this angle here, if we call this theta, is also decreasing, right? So it's kind of more accurate to recognize that as a function. So our theta is decreasing as time goes on as well. And the first thing that the problem actually even said was that the ladder is 6 feet or 16 feet long. It is a 16-foot ladder. So this length is 16 feet. Great. So I'm going to erase the other pictures that are just showing us like what's happening over time. And we're going to identify and give names to some of these parts, right? So this side of our triangle, I'm going to call h of t, right? Like how high the ladder is. And I don't know a better name than this. I'll call this g of t, the length on the ground, right? And so this tells us that because it's falling at a rate of 4 feet per second, then h prime of t I can say is negative 4, right? Because this height is decreasing, then that derivative should be negative, is one way to look at it. Now, the next piece is the actual question that it's asking us. At what rate is the bottom of the ladder sliding away from the wall at the moment when the top of the ladder is 12 feet from the ground? So at what rate is the bottom of the ladder sliding away from the wall? Well, we recognize at the distance from the bottom of the ladder to the wall is the function that I named g of t. And so it wants g prime of t when the height is 12 feet. When the top of the ladder, h of t, is equal to 12. So we're going to say let t naught be this value. So we really want to find t naught where t naught is the value where the height is 12. So first of all, we can look at the sides of this triangle as they relate to each other, right? When we're talking about sides of a triangle, one of the most natural things to bring up is the Pythagorean theorem, right? Well, especially a right triangle. So a squared plus b squared is equal to c squared. Well, if instead a, b, and c are all functions of time, then this is something that now we can do in our implicit differentiation on, or chain rule, whatever the words we want to call it. This 2a times a prime of t plus 2b times b prime is equal to 2c of t, c prime of t. So that's just this very general form, right? However, for us, it turns out because the height, or the length of the ladder itself isn't changing, and that's the part that we would call the hypotenuse here, right? Because this is going to be our right angle in the inside corner with the building and the ground. So it turns out we would write in our terms g squared plus h squared is always going to be equal to 16 squared. So when we differentiate this, we have 2g of t, g prime of t, plus 2h, h prime of t is equal to, well, this turns into 0, right? 16 squared is still some constant number, so when we take that derivative, we're still going to be 0. And sometimes, right, we will know the exact value. So, right, we know that we're going to let h of t be equal to 12. But if I wrote g of t squared plus h of t, but I know that h is going to be 12 squared is equal to 16 squared, then I end up taking this derivative and would get 0 for this. I'd be ignoring the fact that there is some change happening. Even though I eventually will be plugging in a 12, I need to acknowledge that our height is still changing. So the fact that the h prime of t there is necessary. However, the length of the ladder is not changing. That is not a function. The height of that ladder genuinely is constant. So setting that equal to 16 and taking that derivative to be 0 is good, right? Perfectly fine and dandy. So now that we have this equation, we actually set this up for t naught. So this is 2 times g of t naught times g prime of t naught plus 2h of t naught times h prime of t naught is equal to 0. Well, we already know a few of these pieces. For one, this whole question is setting up h of t naught needs to be 12, right? So this is 2 times 12. Well, the question itself told us at the start that the top of the ladder slides down the wall at a constant rate of 4 feet per second. So, that recognition that I made earlier, h prime of t is negative 4. So we have a negative 4 right there. So that is equal to 0. And we don't quite have yet what g of t naught is. And g prime of t naught is what we're trying to find. So I said we don't have g of t naught, but it turns out, because of our Pythagorean theorem, that we can find it. So g of t naught squared plus h of t naught squared has to be equal to 16, but h of t naught, right, is 12, so we really have, oh, and 16 squared, right? So we really have g of t naught squared plus 12 squared equals 16 squared. So I can just absolutely solve for g of t naught, right? 16 squared, I'm opening a calculator. 16 times 16, 256. Oh, I knew that. I didn't know that. Minus 144 minus 12 squared gives me 112 squared. And when I take the square root of that, I get about 10.58. So I already skipped over some of the work. We take the square root and we get g of t naught is about 10.58. So now, putting that value into our equation, it turns out the only unknown is g prime. So we can go ahead and solve for that. We're going to move this to the other side of the equation. I guess we can multiply it together too, right? 2 times negative 4 is negative 8. Negative 8 times 12 is negative 96. And we can go ahead and plug in 10.58. And when we multiply that by 2, I'm getting ahead of myself. So we can move the 96 over, so that I have g prime of t naught times 2 times 10.58 should be 21.16, I think, right? 10, no, 10.58 times 2, 21.16, incredible. Now, this is equal to positive 96, so g prime of t naught is 96 over 21.16, which we can simplify. 96 divided by 21.16, 4.54-ish. So this is about 4.54. That is the worst wiggly equal sign that I've ever seen. About 4.54. And again, because this is a word problem, we need units, and we're working with feet and minutes, sorry, feet and seconds, right? That's what the original problem told us. Feet and seconds. So we're still going to be working with feet and seconds. So this is 4.54 feet per second. Now the last problem we had square meters because we had an area, right? But this is just a distance, right? So that's still feet. Okay, so that's part A of this problem. So the next kind of problem that we can ask is let theta be the acute angle formed between the ground and the ladder. How quickly is theta changing at the same moment referenced in part A, that is when the top of the ladder is 12 feet above the ground? So this is saying at that same moment, right, or t naught, where h of t naught is 12, it wants to know theta prime of t naught, right? Because theta on its own is some function in terms of time, like we discussed at the start of the problem. So to talk about the change, then we want theta prime at t naught, or the change at that moment that they mentioned earlier. So how can we relate theta with some stuff in the triangle that we already see? Well, if I write SOHCAHTOA to remind us of the rules, right? Sine of an angle should be the opposite over hypotenuse. Cosine of an angle should be adjacent over the hypotenuse. And tangent of the angle should be opposite over adjacent. So all these ratios sitting inside of our triangle. Well, which one of these ratios are useful for us in this question? So that is, I know that I can look at sine of theta, cosine of theta, and tangent of theta, but probably one of these is going to be more relevant to what we want than the others. And it turns out, right, that if we were to take, or if we were to look at all of these, then, right, for theta, the opposite side is h, and hypotenuse is 16. So sine is h over 16. Cosine is g of t is the adjacent side over 16. And then tangent is opposite over adjacent, so h over g. So when I took the derivative, or if we were to take these derivatives, sines would involve h prime, cosine would involve g prime, and tangent would be a quotient rule involving both. Well, which of these do I know? Do I know g prime or do I know h prime? Well, and it turns out, because of the setup of the question, we know both, right? Because part A was all about figuring out what is g prime at t naught, right? And we figured out it was this. However, the question gives us h prime. So it might be more natural in that case to say maybe, there was a lot of work that went into G prime. If we don't trust the work that we did, let's check and see if maybe, or let's be careful and use the H prime that they gave us, right? So I say sine of theta is H of t over 16. And again, I'm technically considering, right, theta is a function of t. So really, sine of theta of t is equal to h of t over 16. So now taking this derivative with respect to t, on the left-hand side we have a chain rule. So derivative of the outside part, derivative of sine is cosine. The inside stays the same. Times the derivative of the inside, well, the derivative of theta of t is theta prime. And this is equal to, well, no, we don't have to use the quotient here because dividing by 16 is really just multiplying by 1/16, right? So really this is just h prime of t over 16. So again, why did we use sine? Because h prime is automatically going to be -4. So this is -4 over 16, which reduces to just -1/4. So what we have so far is cosine of theta of t times t prime of t is equal to -1/4. So the only unknown right now is, well, the thing that we're trying to solve for and theta of t. But really we're considering cosine of theta of t. Well, if we're looking at the triangle at this moment, then we have 16 and 12 right here. and this is our theta, right, of t naught, if everything is at this moment t naught. So can I figure out what cosine is based on this? Well, yeah, that rule that we wrote earlier. Cosine of theta should be opposite. Wait, nope, nope, that was sine. CAH, adjacent over hypotenuse. Well, the adjacent is just g of t naught, so we just need to figure out what g of t naught is. Well, again, we have 16 and we have 12, so Pythagorean theorem says g of t naught squared plus 12 squared is equal to 16 squared. And we did this work already up here, right? To find that square root of g of t ended up turning into 10.58 is g of t naught. So this is our adjacent, which means cosine of theta is 10.58 over 16. And now this times theta prime of t is equal to negative 1/4. So just multiply by this reciprocal, and the change of the angle at that moment, right, is negative 1/4 times 16 over 10.58. And now this 4 cancels with this and leaves us with 4 on top. So this is really negative 4 over 10.58. Very good. So this angle theta, and we can simplify this out to something else if we had a calculator. Um, and I do, but I don't think showing what that equals to is so horribly important to us at this juncture. Very good. So that is enough of this latter question, I would say. So the next question that we're considering is this. Oh, a water tank has the shape of an inverted circular cone with a base radius 4 feet and a height 10 feet. If water is being pumped into the tank at a rate of 10 cubic feet per minute, how fast is the water level rising when the water is 5 feet deep? Hint, the volume of a cone is 1/3 pi times the radius squared times the height. Okay, so let's do our best to comprehend whatever it was that it just told us. So it tells us that we have an inverted circular cone. Well, a circular cone is just the cone as we normally think about it. And to say it's inverted just means that it's sitting on the tip like that. So immediately, this is way too small for what we're going to draw. So immediately this problem isn't very practical because how often do you have tanks full of water sitting on such a tiny point like this? You don't. But regardless, this question is a lot easier than if the cone was flipped upside down. I'll tell you that much at least. Okay, so this is getting filled with water, right? And it's going to look like that. Well, what we know so far is that the radius of this is 4. The height of the cone, I believe it said, was 10. And we know the water is being pumped into the tank at a rate of 10 cubic feet per minute. How fast is the water level rising when the water is 5 feet deep? And then it tells us the volume of a cone. So the volume of a cone, right, if we're going to say V of t, well, hold on. Just regular volume of a cone is worth writing down. Volume is 1/3 pi times r squared times the height. Okay. Now, the idea here is that water is being pumped into the cone, right? We're filling up the cone. And it immediately is going to the bottom, which is why I draw it here. And so the water sitting inside of the cone is really making its own cone, right? So it has its own radius and it has its own height. And this says, the question says, water is being pumped into the tank at a rate of 10 cubic feet per minute. So that is telling you the volume of water that is being added. So the change in the water's volume is 10 cubic feet per minute. Okay, now it wants to know how fast is the water level rising when the water is 5 feet deep. So we want something about the change in height of this portion of water, right? So first what we can do is say, okay, well, if volume, right, is changing with respect to time, then really we know the radius is changing with respect to time and the height is changing with respect to time, right? As this cone is getting filled, the radius of the cone of water as it sits inside is getting bigger and also the height is changing as well. So we would want to set it up like this. Now v prime of t is going to be 1/3. Now our chain rule says bring the 2 down, leave the inside alone, and then multiply by the derivative of the inside. And then, oh, wait, sorry, I got way ahead of myself. So I got too caught up in doing all of our chain rule work, right? But, okay, this is going to spin out to be something a little bit gross, so I'm going to simplify things before uh, we get to the next part. So the thing that I need to point out in order to make this problem even doable is that this cone of the water is sitting inside of the big cone, which means the two triangles, right, the cones themselves are similar. So what we mean by that, right, is the triangle sitting inside of this cone, right, matches the big triangle of the outside cone. They are similar. So, even though they're both changing, I know that the ratio of h to r, right, h over r, has to match the ratio of the big radius and the big height, right? So h over r has to be equal to the big H and the big R, which in this case are 4 and 10. So I can rewrite R or H purely in terms of the other, thanks to this setup, right? H of t over R of t has to be equal to 10 over 4. We have to keep this ratio. So I can replace either one. However, we should be conscious about how we end up doing this replacement. If I write h of t is equal to 10 r of t over 4, or 10/4 times r of t, then I am going to replace h of t in this function and only end up with things in terms of r. However, the question doesn't want something about how the radius is changing. The question wants how fast is the water level rising. So it wants the height of that smaller circle. So that tells us we don't want to replace h of t, we want to keep h of t. So instead, we're going to write r of t. Now the way that this is immediately set up is right a little tricky, um, but maybe going from this equation to this one is not too bad, right? How do we get rid of the 10 over 4? We multiply by 4 over 10. So r of t is equal to 4 over 10 times h of t. Now I plug that in. I drew the arrow to the absolute wrong point. Now I can plug that in and get v of t is 1/3 4 over 10 times h of t squared times h of t. Well, 4/10 squared gives me 16 over 100. And then we're going to end up with 3 h's. So really v of t is 1/3 times 16 over 100 times h cubed. So now I can take this derivative and it's going to be a lot simpler. So this 3, sorry, I keep getting ahead of myself. So the 1/3 and the 16 over 100 is going to stick around. Now I use the chain rule on this h of t cubed, and that turns into 3 h of t squared times the derivative of the inside is h prime of t. And I can simplify this just a little bit. 1/3 times 3 cancels, 16 over 100, h of t squared times h prime of t. So, right now, there's two unknown pieces, or right, the way we look at it right now, it looks like there's three. However, we know that the volume is filling up at a rate of 10 cubic feet per minute. So really, it's not just v prime of t equals this. We know that v prime of t is going to be 10. So now the only unknown that I actually need to figure out is whatever h of t is. However, what is the question even asking us in the first place? How fast is the water level rising when the water is 5 feet deep? So, what is my height when the height is 5 feet? That is exactly 5 feet. So, 10 is equal to 16 over 100 times 5 squared times h prime of t. Now, 5 times 5 is 25, so 25 over 100 times 16 times h prime of t is equal to 10. Well, 25 over 100 is 1/4, and 1/4 times 16 is actually just 4. So really we have h prime of t is equal to 10. Sorry, 10 is equal to 4 h prime of t, so h prime is equal to 10 over 4. Okay, very good. So how fast is the water level rising when the water is 5 feet deep? 10 fourths cubic feet per minute. Oh, sorry. Water level is just going to be feet. Right, that is a normal distance. Um, right, height gives you feet, so h prime gives you feet per minute. Very good. And I was looking at my answer, and I thought, this just doesn't look quite right. Um, and I realized I forgot to write the pi. So I wrote this pi at the very top, and I forgot to write it in the actual equation when it came time to use it. So really there should be a times pi just sticking around um, everywhere. And because we're taking derivatives and whatever, um, that times pi is just going to keep following us around at every point. So once we get here, um, when we solve for h prime of t, we need to divide both sides by 4 and pi. So really this is 10 divided by 4 pi. Okay, so that was a really tiny mistake that um, hopefully would be very small if it was a tick off of the grade. Um, but yeah, pi. Don't forget pi. Hopefully you thought he's doing something wrong as you watched me do this, because there should be a pi somewhere. And there did need to be a pi somewhere. Also, as much as I simplify things, I don't know why I'm not going to simplify 10 over 4, right? We can cancel a 2 and pull this out. So really this is 5 over 2 pi feet per minute. Okay. Yeah. Whenever you're having circular stuff, pi should show up somewhere, unless things just happen to be working that nicely. So it felt weird there was no pi. Okay, so very good. That now that really is enough of the cone mess.